Good morning to everybody, and thank you for joining this workshop organized by the De facto project. During the next almost 3 hours, we'll be talking about the digitalization or digital approach in the battery development. Let me introduce myself. My name is Idoia Urdanpilleta. I work for CIDETEC, and I will be leading this workshop in collaboration with two of my colleagues, Elisabete Ayerbe and Maria Yanez. Elisabete Ayerbe, she is the De facto project coordinator, and Maria Yanez is the De facto project manager. So, few remarks before we start. The workshop will be recorded, and the recordings will be available after the end of the meeting. Please be sure that you are muted during the talks. To interact with the speakers, you will have available the chat. So please, if you want to make a question to the speakers, use this chat. Don't turn on the camera unless we indicate that. And if you have any technical issues, you can contact our main host using the private chat, or you can write an email to the address that you can see in the screen here. So this is the agenda of today. We'll start with a short introduction, followed by an overview of the European battery research activities. After that, we'll have a short session with different talks about the LC-BAT projects. In total, we'll have 7 different talks. We'll take a couple of questions, 1 or 2 questions, depending on the time for each talk after the talk. After that, we'll have an active break. We indicate here that it will be active because my colleague Maria will explain you how to get comfortable using the Menti.com program. Okay, this is a program that we'll need in the second part of the workshop. After that, Christina Estrom will give us an overview of the Batteries 2030 Plus initiative. And before we go, we break out in different rooms. We want to show you a video about a digital solution that we have developed here in CIDETEC for cell design. We think that this information can have some interest in the areas. So as I mentioned, we'll after the video, we'll break out in 4 different rooms. In each room, we will discuss one specific topic, and we'll have a live Q&A session. Each room will be moderated by a very well-known expert on the topic. In the first room, we'll be discussing about the artificial intelligence for data analysis. In the second room, we'll discuss about the digitalization in the battery manufacturing. In the third one, about the digitalization in the battery design. And in the fourth one, the digitalization in the battery control. After these parallel sessions, we'll all come back to the main room for a wrap-up and conclusions. So it's time to start the workshop. So I will pass the word to my colleague, Oscar Miguel.
Thank you very much, Idoia. Good afternoon. That is challenging the way we do science, technology, the way industry works, services. And this is also true for batteries. That's why we are here today. Here in CIDETEC, we have been working in batteries for nearly 25 years so far. Oh, sorry, I think. Yeah, no. Yeah, I was telling you that here in CIDETEC, we have been working for nearly 25 years in batteries so far. It is true that the second half of this time with much more intensity. And the way we have been approaching this field has been very much focused into technology development, upscaling, prototyping, testing, validation, and so on. All this is very much needed to make progress, but it's very time consuming, it's very prone to trial and error, and generates a lot of valuable data that you can use. So at some point in the past, a few years ago, some colleagues here in the team proposed to start focusing in modeling and simulation for batteries. This is something that we need to thank to my colleagues here today, Idoia and Elisabeth mainly, and as well as others. And it was a kind of challenging idea because that was something quite new here in our team. And after that, we have been continuing in this effort. And today, I'm very proud and very happy to see that we are hosting this webinar as coordinators of the De Facto project, which is the first European-funded project entirely dedicated to modeling and simulation of the battery cell production line and processes. Also, I'm also very happy and proud to see that we are active members in 4 out of 8 projects and initiatives to be displayed today. So, I mean, I will take the opportunity also to thank 3Believe, Hydra, Sense, and Modalis projects, as well as LeapPlanet and Battery 20+. Moreover, as my colleague Idoia has introduced, we will present for the first time the new tool that we are developing to modelize and simulate cells, starting from all the internal components and features contained there. But I will leave this for my colleagues later on. So all in all, I think today we have very good opportunity to align these efforts in these workshops to combine the different views from these different initiatives. So I'm quite anxious to see the outcome of today, and I hope you will enjoy as well as I hope to do. So thank you very much for attending. I wish you a very good workshop, and that's all. Thank you very much. Idoia, the floor is yours again.
Thank you very much, Oscar. So, let's welcome our first speaker, that is Luca Feola. He is a European project officer, and he will give us an overview of the European battery research activities. So, Luca, whenever you want.
Yes, thank you, Idoia. Look, I will share my screen because I prepared a short presentation for this subject. And then please tell me if you can all see it.
Yes, we can see Luca.
Okay. Okay. Well, thank you once again for inviting me to this, let's say, very exciting workshop. With this presentation, I just want to give an overview of the battery research activities. Maybe I will start from the background of what happened some years ago, trying to understand from where we came from until today, and what's also the outlook of the future in terms of research activities funded by the European Commission. I would say that if we look back to October 2017, that's probably where it all started with at that time Commissioner Šefčovič, who launched the European Battery Alliance. This was an initiative due to the, let's say, to the increasing pressure toward the European industry to be more competitive in the battery value chain due to the presence in the European market of, for instance, other producers of battery, due to the dominance, for instance, of Asian markets. So at that time, the idea was to start this battery alliance. This was from October 2017, which was formalized in May 2018 with European Commission releases of the communication and the so-called Strategic Action Plan for Batteries, which became the legal foundation of these activities. So what were the 6 challenges which were laid at that time related to the battery research activities? One was related to the access raw material also outside of the EU. The second one was to support European battery cells manufacturing at scales and to have a full competitive value chain in Europe. The third one was to strengthen industrial leadership through stepping up EU research and innovation. Fourth one was to develop and strengthen a high-skilled workforce in all the sections of the value chain. The fifth one was to support the sustainability of these activities, I would say, in general. And the sixth one was to ensure consistency with broader enabling and regulatory framework related to batteries. So let's say these were the 6 pillars laid at the time of the European Battery Alliance Foundation. How did this translate into action? What are the actions that have been implemented, or let's say through which tools these pillars wanted to be achieved? So the tools have been mostly funding projects through different platforms, I would say. Definitely Horizon 2020 has played a role. There has been specific battery calls launched since 2018. Battery Europe, European Technology and Innovation Platform has been founded. This is the specific platform for the European Battery Alliance to, let's say, develop the path on research on this subject. Horizon Europe, which is the continuation of Horizon 2020, will keep on allocating EU funding through specific topic on batteries, and we will see more later on. Also, there has been, I would say, specific projects such as Battery 2030, which we will see later on in the presentation today, with the purpose of gathering research in Europe to obtain results on these the major technical advances. On top of this, there has been also launch of so-called important projects of European common interest. I would say these 5 probably are the ones where I've been the most involved, but there are several more actions at a broader range, also involving directly member states, potentially also citizens, and the whole list of action is there. I would say these 5 are probably the one that are also more related to the workshop of today. So if we go into the detail of, for instance, activities under Horizon 2020, officially it started in May 2018 with the first allocation of 115 million euros made available for the first battery-specific topics. Prior to this, there were battery-specific topics, but these were under Green Vehicles Call, and also I would say, not so clearly related to battery related, definitely not related to, for instance, cells development in the specific as we have in those topics here. So in 2019, there were 7 topics. And we see the last 3, which I highlighted here, are the topics for which we have the project presenting after my introductions. So the 7th topic counted for 114 million euros, and it represented a total of 20 projects funded throughout the period of 2019. This then continued last year with another round of financing of 132 million euros, which resulted in 8 topics this time, for a total of 22 projects funded. Here we have the details, and as we can see, somehow it looks like an addition of what was already researched in the previous years. Let's look now at what will be in the future. Sorry, what's in the future for Horizon Europe. In short, the work program now has been already published as a draft. However, it's not yet adopted. But what we can see is that there are foreseen 8 topics in 2021 with an overall budget of 160 million euros for a total of 21 projects expected to be funded. And in the next year, again in 2022, there will be 10 topics for a budget available of 133 million euros, and the expected project to be funded is 23. I would say the key takeaway of the last three slides that I presented is that from when this all started from 2018, as you can see, there has been an increased number of topics available throughout the years, an increased number of projects funded, and also an increased number of the available budget throughout the years. So I would say that this represents the fact that these kind of research activities have become more and more important. Some specific topics have been allocated, new activities to research and to agree on these topics, such as the battery partnership, have been set up. And I think, yes, these activities are here to stay, and we will see more and more also in the future after 2022.
Luca, you have just 2 minutes left.
Okay, actually, I am done.
Okay, good. Thank you.
So I'm done with the presentation. I would say with the next presentations by the project, yes, we will see more in details of what currently these projects have been made available in terms of research activity for the digitalization of battery research. So thank you very much, and let me know if you have some questions. Thank you.
Okay, thank you very much, Luca. Now my colleague Elisabete will take care of the questions. I don't know if we have any question, Eli.
I don't see any questions in the chat regarding your talk. Anyway, what you already mentioned that you expect to have an increase in the budget allocated to the battery. Maybe which is the expectation in the increase? And I mean, shall we something? Can you give us like an overall approach in this increase, for instance?
I'd say mine was mostly a reflection of what has happened in the last 3 years now, from 2018. To be honest, the budget for 2021-22 has just been approved. To be honest, I cannot make a forecast of what the budget will be in 2023-2024. Just what I wanted to say is that from what we see, the trend is an increasing trend in terms of budget allocation and project funded. I think and I hope the trend remains the same, just that from now I cannot really say any number, I would say.
Okay.
Not because I don't want, but because it depends on several other factors, of course.
Yeah, we completely understand your point. Yeah. Thank you.
Okay, thank you very much, Luca.
Thank you.
So now we'll go into the session of the different LC-BATA projects. And our first speaker is my colleague Elisabete Ayerbe, and as I mentioned before, she is the de facto project coordinator. So Eli, whenever you want.
Yeah, I hope you can see me and also listen to me properly. I would like to now, I hope you can see the slides.
Yeah, we can see Eli.
Okay, perfect. Thank you. So thank you for the introduction, Idoia. I will talk about the latest results in the de facto project, pursuing the accelerating battery developments by means of multiphysics models. But let me first introduce the de facto project. When we talk about de facto, we say that it goes towards digitalization of the lithium-ion battery cell manufacturing plant. And when we mention digitalization, we mention that it's approaching, because basically digitalization is relying on three main pillars. First one is the data handling, data storing, data collection, and even data analysis. The other pillar is the communication, that deals the communication between machine and machine, real assets to the virtual assets, or somehow it should be considered aspects on Internet of Things, of device security, and so on. And then the third pillar is on the modeling. So we at the de facto project, we are developing models capable to reproduce the manufacturing plant, and we basically will be concentrated on the main step of the manufacturing, basically on the electrode production, some of the cell assembly, dealing with electrolyte filling, and even closing the loop with the aging and performance prediction. So now I will show the later results. So I will start with the electrode processing. We basically cover the full value chain in the electrode processes. We deal with this dispersing, slurry preparation, drying, and calendering. So when it comes to the dispersing, we have the carbon black agglomerate size distribution, and this information defines the rheological properties of the slurry. So it's really important. Sorry. Yeah, I just, okay. Yes, and this carbon black agglomerate size distribution is a critical factor defining rheological properties. So within the factor, we have our colleagues develop and resolve CFD-DM simulation. And through this simulation, I'm able to predict final agglomerate size distribution depending on the shear stress. Now, coming to the drying step and considering this agglomerate size distribution, we can implement CFD-DM simulation in both scales and resolve it. And we are able to track the evolution of the electrode thicknesses and porosity, depending on the mass loading. And then coming to the calendering step, we have already developed the DEM simulation, in which the adhesion properties to the current collector are already inserted, and even we are able to track the heating of the rollers inserted in the calendering. So with this taken into account, we are able to control the whole process of the electrode manufacturing. Now coming to the electrolyte filling, the aim is to understand properly this step, because mainly it's a very time-consuming step. And even there are certain parameters like the wettability of the electrolyte, which is a critical factor that affects the durability of the cells. So meaning that we need to properly address this factor in order to enhance somehow the lifetime of the cell. So basically, we rely on the lattice-Boltzmann simulation approach, and our colleagues developing the simulations have already included a setup in which they applied a pressure gradient into the virtual cathode structure, and then they gain understanding on how electrode porosity and wetting behavior are influencing on the outcomes. Then on the right side, you can see a picture in which we can draw the saturation plots, pressure saturation plot, gaining understanding on and even optimizing the parameters. Like we know exactly how the wetting factor is affecting include, and as well as the porosity. Then once the electrolyte filling is done, and then we assemble the cell after the formation step, we know that the cells, the repeated cycles are degraded. And in particular, in the de facto project, we will be dealing with the silicon anodes, in which this silicon is addressing like expansion and contraction phenomena, and this might cause some stresses and modify the structure of the electrode, causing somehow premature degradation like the lamination, cracking, and so on. So within the de facto will be concentrated on the mechanical properties and how these properties are affecting the mechanical degradation are already linked to the electrochemical degradation. So basically we solve from the multi-scale approach, coming from the atomistic, then going through the mesoscale, and then going up to the continuous scale. From the atomistic, we get more on the insight on the mechanical properties of the silicon, depending on the lithiation state. We've been also working on the homogenization techniques with the silicon carbon composite material. And then our colleagues are also coupling electrochemical and mechanical models in order to track properly the impact on the mechanical aspects and the stress on the electrochemical performance. And then we are running continuous scale, large cell scale or continuous scale models as well. So once we have these continuous scale models, the aim is basically to propose an optimized cell design, basically with these accurate models, and even we are capable to track and correlate these optimum cell design properties together with the manufacturing processes. So basically we aim to have this continuous scale models, and considering this that they have a very large computational cost, we aim to build the reduced order models. Basically we aim to implement two approaches. The first one is like a regression approach, the other one is based on the reduction of order methods. So with these reduced models, we then implement optimization algorithms, even sensitivity analysis in order to evaluate and to anticipate the critical parameters in here. And then we can explore different configuration of the geometry of the cells and even the cell components. And the good thing is that we will be able to track and correlate these design parameters to the manufacturing parameters. Now here you can see a plot in which they have been implementing reduce all the methods into the P2D model. Now you can see that exactly this reduced model mimics the full P2D model behavior, and the good thing is that the computational burden is reduced by a factor of 10, which is very important for performing optimization algorithms. Nevertheless, I have to say that we are currently define the optimization algorithms. So basically we aim to increase energy density, cycle life, and then we have to set some constraints as well. So when we do this these optimizations, we need to rely on the experimental data, and the experimental data will be obtained within the whole domains, starting from materials, coming to the electrodes, and then going to the cells. So basically, the aim is also to track the uncharacterized intermediate products along the manufacturing process. So,
Eli, sorry to interrupt you. You have a couple of minutes left.
Okay, thank you. Okay, so I was saying that we have already started working on the identification on the structure and composition of certain materials. We have already started analyzing the electrode, getting the tortuosity by the electrochemical characterization, and linking this to the pore distribution side. And then also we have set up a facility to investigate the electrolyte filling process and start defining the test matrix for the electrochemical test. So electrochemical test, aging test that will be done to a pouch cells, and there will be two kind of pouch cells. One is coming from the prototype pilot lines, and it's what we call prototype scale cells, and the other one, it will be manufactured by an industrial partner, and it's commercial cell, graphite NMC 622. So we will be having a comparison between the two scales, and also we are currently inserting implementing sensors throughout the production line in order to get data monitoring of the manufacturing process. So with this, I would like to thank the whole consortium. We are 13 partners around different EU countries, and yeah, and I'm at your disposal if you want to make any question. Otherwise, you can reach me in this email account. Thank you.
Thank you very much, Ellie. We don't see any question in the chat, so please use the chat if you want to interact with the different speakers. Just write the question over there, and we will collect and we will make the question to each panelist. So Ellie, I have one question over the project. I guess that you will be generating a lot of data, and my question is, you will, or this all this data will be available in the future for the battery community?
The first, we aim to store all the data. I mean, we aim to build one database, and this database basically will come from experimental raw data, and in principle will be available within the duration of the project. So if you are interested, I mean, if anyone is interested in the outcomes of the project and want to see any data, you can reach us and we will be sharing this.
Okay, thank you very much, Ellie. So let's jump to our next speaker. He's Luis Trilla. He's coming from IREC, and he is the COBRA coordinator. So yeah. Luis, the floor is yours.
Okay, excellent. Thank you. I'm going to share screen. All right.
We see the screen, please.
Can you see it? Okay, excellent. Wait a second. I'm activating the camera. Okay. Can you see it okay, correctly?
Yes.
Yes. All right. Thank you. Well, I am going to present here the approach of the COBRA project regarding the use of advanced models and sensors. Just for a bit of introduction, okay, in the current state of technology, what we use is the equivalent circuit model, okay, to have an estimation of the state of charge or state of health, for instance, of the cells. This is a good approach because of the simplicity of the model, just allows it to operate in real time and in embedded systems like the battery management system. Okay, but however, with this kind of control systems, what we don't have is any information about what is happening inside of the cell. So on the other side, what we have is these advanced models. In the COBRA project, we are aiming at the physics-based model, which actually requires a good knowledge of the equations governing the chemical reactions inside the cell. So in this way, what we can do is to have information about the mechanism that are making the cell aging, for instance. And we understand that in the future BMS, these kind of models will be used in order to optimize the use of the battery and to minimize its degradation. The issue here is that these models are typically very complex, or at least excessively complex for a real-time application. And then there have to be some sort of a strategy to derive this complex model to something that is the reduced order model in order to develop some control algorithm that can be running an embedded system. Of course, there are other approaches like the data-driven models. This is some sort of a black box where well, you are training an artificial intelligence algorithm with a large set of data, for instance, gathered from testing batteries. And also there are in-betweens, which are called a gray box, and a mix of these two strategies. Well, in the physics-based model, in the full order model, what we do is to define the geometry for the components, the cathode, anode, electrolyte, and so on, then define a meshing, and then we have to put here all the conditions and the physics involved for this exchange of ions. There are well, some applications like analyzing the aging process, or even reducing the effort in aging tests, optimizing cooling systems, or analyzing these complex phenomena that happen inside of the cell. But since what we want is to run this kind of model in some embedded system, what we have to do is aim to this reduce order model, which what we have to do is to reduce the complexity of the model, but still capturing some of these key phenomena. And then we can use it online, this kind of algorithms, for instance, for a charge management control. And during the charging of the battery, what we can do is optimize it by reducing the impact of the degradation of the battery. Then on the other side, well, we have a novel amount of sensors that are proposed for batteries. Of course, we have the standards, the voltage, temperature, and current, but there are many others like the strain gauge or the EIS, the electrochemical impedance spectroscopy, pressure, gas detection, humidity, others, there are many. And also they can be placed on the cell or sometimes inside the cell. There are these two options. Well, here in the Cobra project, what we are trying is to improve this, what we call the smart cell functionalities, like providing some sort of small brain to the cell just to handle itself and provide useful information for the BMS. So just some examples, for instance, the EIS sensor. It can be used to gather information and estimate the core temperature of the cell. This is something very important, for instance, for fast charging strategies. Also, it can detect the thermal runaway, so early detection of failures, very important from the safety point of view, but it can also provide information about the state of health. Here you can see some of the main features of the prototype that's under development, some pictures here and some preliminary results. And we have also the strain gauge. Here, what we are measuring is the mechanical deformation, because the cells have this swelling, changing of volume, when they are at different, for instance, state of charge. So we can provide some inputs to the model just to identify correctly what is the state of charge, but it can also prevent an excessive of swelling, for instance, if it can indicate that there's a danger behind. Here you can see some images of the prototypes and the development. And well, here, for instance, one of the challenges is the attaching the sensor to the cell, which currently is a 15-step process, but it can be automated and we are working towards that line. And here is the line of development. For instance, we have the sensor itself and some analog front end, which is under test right now. And the next steps, it's adding a microcontroller to process the information and transmit it to the battery management system. For instance, we have also a multi-gas sensor, and this is based on laser technology. Depending on the wavelength, it can detect a different type of gases. This is something important from the safety point of view, because of course there can be some problem inside the battery if some type of gas is detected. But here the features that we are aiming is to make a prototype compatible for mass production that can be miniaturized. This is very important for the automotive sector, of course, and that is very accurate. In this case, the concentration that can detect is down to 1 ppm, so it can trigger an alarm very early before something hazardous is happening. Here, there's also a picture of the prototype and the development, and the main components are depicted. And we have here an example of this twofold approach, because we are developing this thermal model of the battery, but also placing sensors, temperature sensors at the cell level, and then we can mix this information. In this way, what we can have is something very accurate, providing information about the temperatures inside the cell and throughout the battery pack. Here are some examples of the application. You can see on this side here how the error, when you are only using your algorithm and your model, it's that we have 1.5 approximately error, the peak error of degrees. But when we are mixing the information from the model and from the sensor, it's 10 times less the error, and it's nearly zero. So this kind of applications. And just a summary of this twofold approach. Well,
Luis, sorry, you have 2 minutes left.
Okay, thank you.
Thank you.
Well, the combination of models and sensors, it's very positive because they provide feedback, but then we can have some advanced estimations, for instance, for early detection of failure, very important from the safety point of view, of course. We can have an extended lifetime because we can estimate the degradation and minimize it. we can provide a higher operational window, have an accurate estimation of the remaining useful life, or even provide information about the cell core temperature, which is important for the fast charging strategy. Also to mention that, well, besides the reduced order model, if, for instance, you are using some other complex model, I think it's interesting just to place it in the cloud and then define some interaction between complex models that are running in the cloud and the local models that are in the BMS. And this is something that it's interesting because it might be aligned with this new directive of the battery passport that it's been mentioned in sessions before. And also just to highlight that in the Cobra project, we think that the best approach is to try to have the minimum amount of sensors, because of course they bring less cost, weight, volume, complexity, and so on, and transmit the less amount of data as possible. And for the advanced model, to have the minimum computational effort, because that's less cost in components, of course, and less energy consumption in the battery. Of course, there are some contradictions between these objectives, and you have to find some trade-off. And just to finalize, well, just to mention that there is a new market coming. It's the second life of batteries, because a large number of batteries, which are currently not fitted for EV applications, will be available in the near future, and they still have some useful life. So from environmental perspective, it's better to extend the useful life rather than manufacturing a new one. And well, the current systems do not perform very well when batteries are at low state of health. And we believe that this can be improved with a twofold approach. And just well, to finalize, just to highlight that all these developments I have mentioned, it's a team effort or the Cobra consortium. You can see here the map of the partners. These are 19 partners, including universities, RTOs, SMEs, enterprises. And well, thank you all for your time and your attention. I believe we are on time.
Yeah, thank you very much, Luis, for the effort and for adjusting to the time.
Yes, so what I can see is there's one question, and it's it says, is the EIS circuit powered by the cell it is connected to?
Yes, yes, of course.
Okay. And then I don't see any other question, but maybe you could, you were saying that you expect to improve the lifetime due to this twofold approach. Do you have an estimation of how you expect to enhance this lifetime?
Not yet. The models and also the sensors are under development, but we are aiming at soon at having the first results of both, and then we will study how the combination can prevent the battery from excessive degradation in different situations, given fast charging or temperature related issues or any kind of issue that can lead the battery to an early degradation, let's say.
Okay, thank you.
Thank you.
Thank you, Luis. Thank you, Eli. So now let's welcome to our next speaker, Boshidar Ganev from IT, and he is the coordinator of the 3Believe project.
Hello, good afternoon.
Hello, good afternoon.
Thank you for the invitation to this workshop. So let me also share my screen. One moment, please. Oops. Okay, can everybody see the screen now?
Yes, we can see.
Okay, so yes, I would like to give you a short overview of a few different aspects of digitalization in the 3Believe project. So of course, like the other projects funded under this call, the overall aim of 3Believe is to deliver performant battery technologies for electric vehicles that can also be produced in Europe and that are compatible or that fit into a circular economy. And for this reason, we take a quite holistic approach across the whole life cycle, almost the whole value chain of batteries, with the exception of raw materials extraction and processing. The project has some activities in almost all the steps along the value chain, and they're grouped very briefly in the following categories. So some of the objectives in the project are to develop an automotive cell on the cell level with a LNMO chemistry on the cathode side and a silicon graphite blend on the anode side, and then a form factor that's fit for passenger vehicles, but also light urban trucks. We also like to integrate multiple types of sensors into the cell, onto the cell, and on module level in order to improve the state estimation or to improve the visibility of different aspects and conditions of the cell. There's also, in terms of the manufacturing, a quality control step that we introduce because the quality of the electrode production can have an impact on the later cell performance. And then at the end, we aim to have demonstrators on cell, module, and pack level. And we aim to show how these can be manufactured on a gigawatt-hour scale. So what can a factory layout look like, and what does the manufacturing process look like? And the project also, as mentioned, wants to demonstrate the developed technologies are fit for a circular economy. So we look at aging both in the first life application in vehicle applications, but then also subsequently in a second life stationary application. So while digitalization is not, let's say, the core topic of the project, it is actually a cross-cutting aspect across almost all of these topics. And I just want to touch briefly on 3 of them. So the first on the battery manufacturing level. So as we know, in the electrode coating process, when it comes to the deposition of the slurry, sometimes it can occur that we have an inhomogeneous deposition of the slurry. So that can lead to coating defects. So that means there can be too little coating in some parts of the electrode or too much material in other parts. And this can manifest as scratches, as pinholes, as cracks, as agglomerations. And the challenge is that both both electrodes, the cathode and the anode, are quite dark materials. So the visual inspection, it is quite difficult, and of course would be very time consuming by eye. So we can employ here an optical image acquisition process that can then also be used, the data that can be acquired from this, in order to then use machine learning to detect the defects and to classify them by defect type. So what can a system for this look like? So in terms of the system, it's a camera with a set of 4 lights that sits at the as part of the electrode coating steps. So after the slurry deposition and the drying process, you have a camera that inspects the coated foil using 4 lights and basically acquires images, and it can compute surface normals and the depth map of the surface. And then, as I showed in the previous slide, detect the various defects. So the aim here is to have this working at higher production speeds and to train the algorithms with the acquired image data to recognize the defects. Then coming to the multi-sensor approach. So like in Cobra, we also employ multiple sensors that beyond voltage, current, and temperature also do EIS measurements, strain or deformation measurements, and can do gas detection. And the first order of business here was to establish a common communication architecture so that the signals acquired from these sensors can all be relayed via a common data bus to the battery management system. So this is one aspect. The other aspect, of course, is that the open source based Fox BMS system had to be updated in order to be able to recognize and process these signals. The second aspect of digitalization with this is that if we think about the measurements coming from all these sensors, if we think about tracking all the different data points over weeks, months, or even years of lifetime of the battery, of course, a lot of data would accumulate. At the same time, the situation is that usually on BMS, there's only a very limited data storage capacity, and this is typically reserved for safety and for performance metrics. So there's very little space for large volumes of cell cycling operational data. But at the same time, this cell cycling history can be very valuable. So for two aspects, so just two examples what can be useful. On one hand, if we think after the end of the first life, a potential second life operator would be quite interested to know how the cell aged. So apart from its state of health, which might be relatively easy to determine, it makes a difference under what conditions it reached this state of health. And therefore having access to such data could help to better estimate for what second life uses such a battery could be put to use. And the second important aspect is for training algorithms. So using the sensor data to train algorithms that can then enable a better state of health or generally other state of X estimation strategies, and that can lead to better operating strategies. So as we heard in the previous presentation, for fast charging, for thermal management, for cell balancing, for example. So this is for the sensors. And by the way, more detail is available in our recently published deliverable 4.1 that's available on the 3Believe website. And then finally, when we have finished the designs on cell, module, and pack level, as mentioned, we like to think about what does the production of this technology look like on a gigawatt-hour scale. And so we start to model the processes. So we think about what does the real-life process look like, what are the necessary parameters, and how can we model this. So for this, it's necessary to model the attributes of machines, some of the input parameters in appropriate simulation modeling software. And so here on the right, you see just one example, just one small subset of the processes. So this is a 2D simulation of notching and lamination and stacking, but really there are many, many more processes that of course can be modeled. The interesting aspect or the takeaway from this is, of course, what questions can be answered with this model. And I've put just a very small subset of the possible questions that could be answered here, but you can think about, okay, what does the layout of the factory need to look like in order to produce a certain volume of cells, modules, or packs? What are the interactions between the different process steps in the production line? How can the material flow be improved? What is the energy use and the corresponding greenhouse gas emissions that result from the production processes? What happens if some of the equipment fails? How much waste output is there in terms of scrap? And so on and so forth. So there's a large list of interesting questions that could be analyzed with a detailed manufacturing process that's modeled. So as you can see, we have a large number of partners, so 21 partners from many different European countries, so 10 different European countries. So I'd also like to extend my thanks for the very good collaboration so far. We are in month 18 of our project, so we have 42 months in total to go. Many of the aspects that I showed in the previous slides are still under development, but of course, when the time comes, we will be publishing results. I should also mention that 3Believe has opted into the open research data pilots, so we absolutely do intend to make some of the testing data sets available to fellow researchers. And so with this, I'd like to thank you very much for your attention, and feel free to visit the 3Believe homepage and social media channels, and I'm happy to take any questions if there are.
Thank you, Boshidar. So Ellie, please.
Yeah, there is a question about, you mentioned the fiber optic surface plasmon resonance sensors. So the question is that where can one get such sensors? Are they commercialized, or is this still in R&D phase? What optical equipment is needed?
So these are, at least the ones being used in the 3Believe project, are still in the R&D phase. So they are contributed by one of the partners. So in this case, it's Insplorion, based in Sweden. And part of the research is to see how to integrate them. What is the output of the measurements? How can we correlate this with other cell cycling data? So I'm not aware that there is something commercially available like this, but I don't claim to have a complete overview of the market, of course.
Okay, thank you. Idoia, I don't know if we have time for another question or not.
No, just I think what I propose is we can collect all the questions from the audience. We will transfer the questions to the speaker, and after the meeting, after the workshop, we can share the answers with the audience, if you agree, just to be able to adjust to the time. Okay.
Yes.
Okay. So thank you very much, Boshidar. Let's jump to our next speaker. He's Simon Clark from SINTEF, and he is the coordinator of the Hydra project. So, Simon, yeah.
Yes. Great, thank you. Good afternoon, everyone. My name is Dr. Simon Clark. I'm a research scientist at SINTEF based in Trondheim, Norway, and the coordinator of the EU project Hydra. Our project has many of the same goals as 3Believe and SENSE and COBRA, the other LCBAT5 projects. So today I'd like to use my time to focus on digital approaches we're using to support model-based battery design optimization activities in our project. So everyone here participating in this workshop has probably slightly different backgrounds, but we're all brought together by the desire to build better batteries. So a good first step could be to think about what is it that we actually need in order to do that. And in an abstract sense, we need a lot of knowledge, right? We need knowledge about electrochemistry and physics and engineering, many different things. We need models that allow us to formalize and quantify that knowledge in some sort of queryable format. And we need experimental data to provide data to support our observations and validate our theories. And of course, these aspects don't really exist independently, but they're linked together in a kind of iterative process. And after we iterate through this enough, eventually we get out some findings or some improvements that are useful to battery design. But the challenge that we face is that this process tends to be rather slow, and the links between these different aspects are not as efficient as they could be.
Sorry to interrupt you. I don't know if you want to share.
Yes, I do.
Okay.
Okay. Well, thank you for stopping me. Let's see. Let's try this again. Who can share? Only host. Okay. How about now?
Yes, perfect. We see your screen now. Thank you.
Great. Okay. Good. So we'll just pick it up from there. So we have different aspects of battery utilization that we need in order to improve batteries. And our challenge is that this kind of iterative process tends to be slow and cumbersome, and the links between these individual aspects are not as efficient as they could be. Digitalization can help. And in my talk today, I'm going to highlight how Hydra is taking these four aspects of digitalization and applying it in our work. So first, I have to put on my Battery 2030 and Big Map hat and talk a bit about the battery interface ontology. So an ontology is a data model that represents knowledge as a set of concepts within a domain and the relationships between those concepts. This is kind of the textbook definition. In practice, that means that here among us and in the battery community generally, we have a lot of experts who have a lot of knowledge. But that knowledge is isolated in people's heads. And if we as researchers or as engineers want access to it, as humans, we can download their papers and read about it and think about it and form new knowledge in our own minds. But that has a couple of problems. A, it's not very efficient, and B, machines can't do that. So that limits the context in which semantic databases or artificial intelligence platforms are able to actually reason over the data that they have access to. So by formalizing that knowledge into a model using an ontology, we get something that looks like this. It's like a map of concepts with relationships between them. And that allows us to query data in both a human and machine readable format. So for us as battery scientists, it brings a few advantages. For people who are interested in data and research data management, it allows for standardization and enables semantic interoperability of different data that you generate in your project. For modelers and software developers, it allows you to build on predefined standard class templates in your software. And for manufacturers and recyclers, this is actually a really great thing to support the battery passport initiatives that are going on now, because it provides a standard description of batteries and their materials and their interfaces, that whether you're a manufacturer creating batteries or an end user generating data or recyclers who want to know what's in your battery, you're all speaking the same battery language and using the same digital descriptors. So with this approach, we can start to formalize all of the knowledge that exists in the battery community and apply it to develop better digital assets. But knowledge is just the first step of the equation. In order to really make it useful and make predictions based on that knowledge, we need some electrochemical simulators. And what are the properties of a good electrochemical simulator? Well, from Hydra's point of view, it starts off by being open source. So it's something that needs to be open to the battery modeling community for quality assurance and for building in new features and improving or standardizing the approach across the community. It needs to be powerful, right? As we've heard, battery models can be very complex. They're not so easy to solve, and it needs to enable dynamic simulations on 1D, 2D, and 3D meshes. It needs to be flexible, so we can minimize the amount of new coding that's necessary if we want to introduce a new feature or design a new system. And we can do that by building on our ontology-based component models. And it needs to be fast, right? We're very impatient people, everybody, and we need models that give us results quickly and can be integrated into real-time simulation workflows. And we can do that by leveraging automatic differentiation and efficient numerical solvers. In Hydra, we're bringing all of this together in a open source battery modeling platform that we call BATMO. So what is BATMO? BATMO is a finite volume continuum modeling framework for electrochemical devices. So with those of you with a background in the field, capable of solving P2D, P3D, P4D models. It's electrochemistry neutral. So of course in Hydra, we're focused on the development of lithium-ion battery models for generation 3B materials and components, but we're not limited to just that. BATMO is flexible and can model post-lithium-ion systems as well as even hydrogen and electrolyzer systems. BATMO is currently implemented with custom solvers in MATLAB to enable it to be very fast and efficient. And we plan to make it even faster by creating an implementation in the open source language Julia. So this is planned for release in summer 2021. When it's available, you can find out more about it at batterymodel.com. So moving forward, I'd like to highlight the experimental database section, starting with a quote. "Data, data, data," he cried impatiently. "I can't make bricks without clay." And who said this? It could be a frustrated PhD student. It could be the PI bursting into your lab. But this was Sherlock Holmes 130 years ago. How little the world has changed. And in Hydra, of course, and in battery digitalization generally, this is true. We need data, data, data. And in our project, we aim to meet this need by doing high throughput testing, both of full-scale cylindrical cells and materials that we develop in the project, and extensive electrochemical characterization of the resulting materials and cells. So we're providing not only characterization cycles, but DQ-DV analysis, electrochemical impedance spectroscopy, GITT, and we're complying to the best practices for research data management outlined in Battery 2030 Plus and BigMap to make this data as far as possible accessible to the research community.
Simon, sorry to interrupt you. You have 2 minutes left.
Yep,
Thank
just
you.
coming to the end.
Good.
So we've been formalizing knowledge, we've been developing models, we're generating experimental data, and now we bring all of this together into a digital battery workflow, where we test batteries and test materials to generate data that's stored in an experimental database and supplemented with data that we're mining from literature and online databases that can then be converted and stored into standardized formats in HDF5 or JSON and stored in a database. Parameters from that database can then be used to inform our models and create a kind of feedback loop with our battery testing activities. So this is the approach that we're taking in Hydra. And of course, this sounds kind of complex. There's a lot of different working aspects to it. And to make it as easy as possible for researchers who are perhaps not comfortable with digitalization, we're creating user-friendly battery apps to help with data processing, parameter extraction, and performance modeling, so that users have to do as little work as possible to get the maximum impact of their data. So just to summarize, battery design requires knowledge, models, and experiments, and digitalization enables the efficient exchange of information in the design process. In our project, knowledge is formalized in an ontology. The modeling ontology is used as a foundation for a flexible, powerful modeling framework. And the characterization ontology is used to ensure the interoperability of experimental data. Data exchange and operations are described in experimental workflows, and within Hydra, we're developing user-friendly battery apps to help make this as accessible and useful to the battery community as possible. If you're interested in learning more, you can visit these websites, bigmap.eu, H2020, hydra.eu, and batterymodel.com to learn more. So thank you for your time and attention.
Thank you very much, Simon.
Thank you for the explanation. There is one question. Is Patmo addressing mechanical issues like impact on expansion in the graphite or silicon anodes on the cell scale, including stress, cracking, and so on?
Yep, that's a function that we haven't added yet, but we plan to work on this fall.
Okay. Do I have more time, Idoia?
No, we are behind the schedule, so yeah. So we'll jump to the next speaker. Thank you again, Simon, for your talk. Our next speaker is Martin Petit from IFPEN, and he is the Model H2 coordinator. Martin, can you switch on the camera? We cannot see you and we cannot hear you.
Can you hear me?
Now we can hear you and we can see you. Thank you.
Okay, great. Thank you very much for the introduction. So I would like to present you some of the results that we have had so far in the Model H2 project. So the Model H2 project is H2020 project dedicated to the modeling of the behavior of next generation batteries, especially Gen 3B batteries and Gen 4 batteries with solid electrolytes. So one of the main issues that we have regarding modeling in batteries is that we are facing a multi-scale behavior, as you know, from the material scale to the system, the global system, and multiple modeling tools are available for each scale. Ab initio modeling are used in order to get some the behavior of the material, especially diffusivities, potentials, mechanical properties. Specific mechanical modeling are also of use at the mesoscale or microstructure scale for the overall swelling of the electrodes, the porosity variations, some stresses on the binder, And one of the main objective is to get the complete cell behavior that we get at the continuum modeling scale. And we are aiming in Modelis to get from this modeling scale the cell swelling, the cell performances in terms of power and energy, and cell aging behavior. So the aim of Modelis is to create ways, passing parameters between these scales and tools in order to be able, from a modification at the material level, to understand the behavior, the global behavior of the cell at the system level, thanks to correlations, Arrhenius laws, and so on, but from the lower scale calculations. In parallel, for all these dedicated modeling approaches, a dedicated experimental campaign is made thanks to devices and facilities that we have in the consortium, as we need dedicated experiments for model calibration and also model validation. This will be done at the same scale as the modeling. That means material scale characterization with microscopy, XRD, granulometry, and so on. Then from the microstructure, we have dedicated electrode characterization with electrochemical analysis, electrochemical dilatometry, symmetric cells for the behavior of the electrolyte. And then we have also developed some dedicated full-scale characterization in order to study the swelling of the full cell with the full cell dilatometer, dedicated aging campaign in order to analyze the aging of the cell. And in this aging campaign, we will have some dedicated tests fit for the final application, that is the automotive application. So as I said earlier, this modeling toolchain is to be developed especially for new battery technologies. There are several already a lot of modeling developments that have been done for classical Gen 3 batteries. But in this project, we want to focus on next generation batteries, especially high content of silicon for the anode in the Gen 3B cells. So as we know, in this case, we will have a higher specific energy, but also a higher mechanical degradation of this electrode due to the behavior of the silicon. So in order to characterize and to analyze this behavior, we will have some ab initio modeling of the material properties in order to get the thermodynamic properties of the silicon oxide of our material for the negative electrode, the thermal and mechanical properties of the silicon oxide, and the transfer properties in the liquid electrolyte, as well as the active material. Then, thanks to this data, we'll be able to perform a mechanical modeling of the negative electrode, giving the swelling of the electrode as a function of state of charge, of C rate, and of the constraint of on the electrode. And finally, applies these two lower level modeling to the continuum modeling in order to assess the performance of the cell. And then once this first development on the Gen 3B will be in motion, we will switch to Gen 4 cells in order to specifically analyze the behavior of the solid electrolyte and the interface between the solid electrolyte and the lithium metal. Several electrolytes will be studied into this project in order to get some generic approaches for this electrolyte modeling. So in order to get information on the behavior of the electrolyte and especially on the electrolytic conduction into this electrolyte, we will have some ab initio modeling of the electrolyte properties, which will investigate the transport numbers and diffusion coefficients of lithium in this electrolyte. And we'll have some dedicated mechanical modeling for the lithium electrolyte interface. And the continuum modeling, as for the Gen 3B, we use this data in order to evaluate the cell performances, the pressure effect, and the safety of the batteries. So in order to perform this work, we will need a lot of different skills. a whole range of modeling scale, experimentation, material manufacture, and battery manufacturing. So in this project, we have gathered all the experts for this this task, and especially members of the European Battery Alliance, so Saft, Solvay, Umicore, and Siemens, who will be the end user of this tool chain. So the expected achievement of this tool chain is to create a seamless interface from nano to macro scales and from nanosecond to years. So I will describe you now the main user case that we want to create during this project in order to demonstrate the possibility of the modeling tool chain. And the first end users are the material manufacturer. So
sorry to interrupt you. You have 2 minutes left.
Okay, I'll be quick. Thank you. So the first one is the Solvay user case, and in this case, they will want to investigate the effect of the electrolytes on the full cell performances. So using ab initio modeling, like GROMACS, they will do some molecular modeling of the electrolytes and apply these results into the full-scale models in order to evaluate the effect of defect and so on the cell behavior. And at the same time, Umicore will do the same thing with the negative electrodes in order to investigate the effect of using specific coating and so on the positive material in order to investigate the behavior of the material at the full cell. Then we have the cell manufacturers, this Saft. They are using the toolchain in order to get better design for their cells. So based on this modeling toolchain, they will want to adapt their process, cell design, and assess the cell behavior, especially looking at the formation steps. What are the effects of fast charges on the batteries and low temperature behavior? Using the battery modeling toolchain, they will be able to assess the cell behavior and especially provide the end users, the car manufacturer, for instance, with control laws for the batteries without any experimental campaign. And then the last end user is the OEM, and especially CMF. They would like to use this toolchain in order to study the effects of mechanical properties using quantum mechanics faults, and also apply this to specific automotive applications duty cycles in order to investigate the cell aging in continuum modeling. So at the moment, we have initiated the development of the toolchain, especially for Gen3B. Ab initio modeling is being performed in order to assess the behavior of positive and negative materials. We are also performing mechanical modeling with FEM and DEM codes in order to simulate the microstructure during charges with high content silicon. And we have developed a framework for the Gen3B battery modeling, taking into account aging, diffusion-induced stresses, and cell swelling. So at the moment, we are just beginning the work on Gen4, but we will prepare a first set of parameters in order to model the electrolytes that are foreseen in the project. And the next steps is to perform this experiments on Gen3B cells in order to feed our models and calibrate and validate the model based on the experimental data. So that's all. It's here all the members of the project. And I thank you all for your attention. If you have any questions, don't hesitate to send me an email.
Thank you, Martin.
Okay, there are several questions. I'm going to take one, and it deals with you will build data coming from the modeling as well as experimental data. Are you aiming to build this specific warehouse in which you aim to share or make it open to the community?
So regarding the data, for experimental data, especially at full cell level, there might be no issue to share this with the community. And the modeling platform that we are using for the moment are modeling platform for Siemens industry software. So it's a commercial software that is being used.
Okay, thank you.
Thank you. So now let's jump to our last speaker from this session of LCBAT projects. The speaker is Deirdre Wolf. He's working in TUBES and he's a coordinator of the LeapPlanet. She's the coordinator of the LeapPlanet project.
Thank you very much. So hopefully you can see my screen now.
Yeah, we do.
Okay. Oops. Can you see the presentation slide still, or?
Yeah, but we see it in the presentation mode. I mean, we don't see full screen.
Okay, sorry, I need to try that again.
Change that display settings.
Okay, so I tried to share this screen. And then, no.
No.
So you can, so if I go display settings, swap. Now
Yeah,
maybe?
Now
Okay, perfect. Okay, thank you.
Thank you.
So yes, my name is Deirdre Wolf, and I am part of the team at TU Braunschweig that works on the LeapPlanet project, which is coordinated by Professor Arno Quada. And he will be actually moderating one of the sessions later in the workshop on digitalization. So within the LeapPlanet project then is looking at a network of research pilot lines for lithium battery cells. The motivation behind the project then was that the European Union must have independent capacity to develop, upscale, and produce batteries, and for this, in order to be competitive on the market. So the battery production lines will play an important role in this to scale up innovations in the manufacturing process and bridge the gap then between the early technology development and mass production. However, in order to maximize the benefits of the European battery-related efforts, there must be a mutual exchange of data, expertise, and access rights between these pilot lines. Yet there so far is not a network that is dedicated to connect the different pilot lines around Europe. And so the aim of the LeapPlanet project then is to establish and develop this network of lithium battery pilot lines and lead towards the creation of a European innovation and production ecosystem. The objectives of the LeapPlanet project then are first to map the research and development battery cell pilot lines around Europe, identify the skill gaps and equipment gaps, develop a roadmap for the network to support European industry, promote the mutual exchange of data and knowledge between network members, provide the training materials and a standard legalized framework for the network, issue recommendations to policymakers, as well as conduct round-robin tests. So the LeapPlanet project, we are currently a consortium of 8 different partners. It is a 2-year project that has been running now for a year and a half and will come to an end at the end of the year. And its main goal then is to lead into the establishment of a sustainable network, which will then be the one-stop shop for the development of sustainable batteries and manufacturing technologies. So the founding of the network has already occurred on the 7th of May, where we have had 8 different members that are now part of the founding of the LeePlanet network. How the structure of the LeePlanet network looks is we have an executive board that can appoint a CEO and also invites an external advisory board to give recommendations on different aspects that are of interest to the LeePlanet network. And this executive board is appointed by the LeePlanet members and has been appointed then on May 7th with the founding of the network. And we currently have the current executive board, the first and the second chairman, as well as the head of communication, the expert groups, and the finances. So the external advisory board is really the interface between the network and stakeholders that span multiple areas of expertise, such as we have members involved in cell manufacturing and digitalization. And as I stated, the external advisory board then is invited to give recommendations into the LeePlanet network. We also have expert group, which are part of the LeePlanet members. And we have held workshops to define as well as redefine really what the expert group topics will be, as well as the subtopics within these expert groups. So the expert groups will facilitate then the exchange between the network members regarding relevant issues. And we currently have 6 expert groups: materials, processing and safety, production, cell design and recyclability, technology and sustainability, education and training, scientific exchange and IP, as well as digitalization, measurement methods, and quality. So we have had already our first initial expert group meetings where the expert group members have elected an expert group chair for each of the 6 different groups that can be seen here. And just to focus in then around digitalization, within these expert groups, we will have crossover between some of the topics that are worked on. However, we also have an expert group that works specifically on digitalization, measurement methods, and quality. And within this expert group, some of the subtopics that will be worked on are, for example, modeling, physics-based, multi-scale, multi-physics, and cyber-physical, machine learning tools, standardization of APIs or data standardization, quality control, and inline measurements. So another aspect that is being currently worked on actually within the LeePlanet project in regards to digitalization is training that is being developed on the benefits and challenges of digitalization in battery production. So this will be organized as a workshop where we have cyber physical production system, data acquisition and management, data analytics and data mining, decision support, and some use cases as topics that will be discussed within the workshop. And this is currently in a very early development stage, and more information on this will be available within the upcoming month. So I leave you here then with just the vision for the LeePlanet for 2030 towards the creation of a European innovation and production ecosystem, where the LeePlanet then will look to be the one-stop shop service provider for education, knowledge transfer, testing, certification, pilot scale production of lithium and post-lithium battery cell technologies for research, industry, and authorities. The LeePlanet network will then empower and develop the development and upscaling of innovative, sustainable, and competitive lithium battery cells and process equipment towards European industrial scale production. So if you have more information regarding the LeePlanet project, please visit our website at leeplanet.eu, where we also publish some of our deliverables that have been written during this first 18 months. So thank you very much.